Hello everyone, this is Organic Chemistry 1, Dr. Sadine's class. We're going to start with Chapter 1 today. And our objectives in this chapter is 1. Atoms plus bonds and Lewis structures, which includes bonds, lone pairs, and formal charges. The third objective is molecular shapes, such as VSEPR theory, bond angles, bond polarity, and molecular polarity. And that includes dipole moments. And the fourth objective is molecular representation, such as Lewis, Kekule, condensed, and skeletal. So first of all, we're going to talk about atoms. The atoms that we're going to use mostly in organic chemistry are carbon, hydrogen, oxygen, nitrogen, and halogens. We're going to show them with X mostly, and sometimes we're going to use sulfur, but rarely. We're not going to use sulfur as much. And the reason we're just using these atoms is because they're non-metals. Non-metals make covalent bonds and they share electrons, while metals usually trade their electrons and make ionic bonds. As you see here, carbon has 4 valence electrons, so they can share 4 electrons and make 4 bonds. So they either can make 4 single bonds, each bond is sharing 1 electron of the carbon. The other version is when the carbon is making 2 single bonds and a double bond. In a double bond, it's sharing 2 electrons with 2 other electrons coming from another atom. For example, oxygen. And the last version of carbon is when we have 1 bond to the carbon and a triple bond attached to it. In this case, the carbon is sharing 1 of its electrons in the single bond and 3 of its electrons in a triple bond with another atom. For example, we could say nitrogen. Now we go to nitrogen. Nitrogen have 3 versions. Basically, the first one is when nitrogen makes 3 single bonds, and it has a lone pair. Don't forget, the reason that we're not having 4 single bonds is because one of them is a lone pair, and lone pair does not make a covalent bond. The second version is when the nitrogen is making 1 single bond and a double bond. And the last version is when the nitrogen is having just 1 triple bond with another atom. For example, carbon, as I already said. Now we go to oxygen. The oxygen has 2 versions. The first one is 2 single bonds, as you can guess. In each bond, it shares 1 electron. The second version, it just has 1 double bond. Now, for halogens, they all have only 1 version, and it is when 1 electron that is available is making a bond with another atom. For example, mostly it's going to be carbon, because the main focus of our study here in organic chemistry is carbon and carbon chains. So mostly halogens are going to make bond with carbons, but that's not like always the case. Sometimes it can make a bond with an oxygen. And as you can see here, hydrogen only has 1 valence electron, so it cannot make more than a single bond. So the point of making a covalent bond is to reach the octet of each atom. Octet means that if you count the shared electrons around an atom, it's going to reach 8 electrons overall. That is not the case for hydrogen though, because it just makes 1 single bond, so it's just going to reach 2 electrons at most when it makes a bond. So as you see here, the carbon has 4 valence electrons. In this case, it can make 4 single bonds, a single bond, and a triple bond, and 2 double bonds. Now, if we add 1 electron to the valence electron, it's going to have 5 electrons overall. In this case, it's going to have 1 lone pair and 3 electrons available for making either 3 single bonds, or a single bond and a double bond, or a triple bond. In this case, we call this a carbanion. And in case you take away 1 electron, it's going to be left with 3 electrons. Now it can make 3 single bonds, a single bond and a double bond, or a triple bond overall. We call this a carbocation, and it is very unstable. If we have a carbon with 3 single bonds and 1 electron left, we're going to call that a radical carbon. Now we go for nitrogen. Nitrogen has overall 5 valence electrons, 1 lone pair and 3 electrons available for either 3 single bonds, a double bond and a single bond, or an overall triple bond. If we add 1 electron to nitrogen, it's going to have 6 valence electrons. Now we're going to have 2 lone pairs and 2 electrons available for either 2 single bonds or 1 double bond. This is the anion of nitrogen. In case you remove one electron from nitrogen, it's going to have 4 valence electrons all available for making 4 single bonds. This is the cation of nitrogen. Now we go to oxygen. Oxygen has 6 valence electrons, 2 lone pairs, and 2 electrons available for making either 2 single bonds or 1 double bond. If you add 1 electron to oxygen, it's going to have 3 lone pairs and only 1 electron available for bonding. This is the anion of oxygen. Now, if you remove 1 electron from the oxygen, one of those 2 lone pairs is going to become single electron and is available for bonding. In this case, you can either have 3 single bonds or a lone pair and a single bond and a double bond. This is the cation of oxygen. So now we're going to go for Lewis structures, and you're going to remember what a formal charge is from General Chemistry 1. A formal charge is when we count valence electrons minus lone pair electrons plus the number of bonds. Now, the first example we're going to go with is CH4O. The first thing we're going to do is to count the overall valence electrons. As you see, C, which is the carbon, has 4 valence electrons, plus we have 4 hydrogen, each of them have 1 electron. 4 plus 4, 8, plus 6, which is for the oxygen. The number of valence electrons for oxygen is 6. Overall, it adds up to 14. Now, we're going to draw this. As you see, carbon is always a central atom. Hydrogen can never be a central atom because it can only make 1 bond, while carbon can make 4. So we make 1 carbon with 3 hydrogens attached to it, and then 1 oxygen, and we don't forget the lone pairs in Lewis structure. Now, there are other structures that you don't need to write the lone pair, but in Lewis structure you have to. And now we have 1 hydrogen left. We attach it to the oxygen because it has 1 electron available for bonding. Now we start counting the formal charge for each central atom. The carbon, the valence electrons is 4, minus it has 4 bonds around it, so we put 4, and how many lone pairs? 0. 4 minus 4 is 0. Now we go for the oxygen. Oxygen has 6 valence electrons, and it has 2 bonds and 4 electrons left for the lone pair. Now, we're not going to put the number of lone pairs, we're going to put the number of electrons in the lone pairs. Each lone pair has 2 electrons. 1, 2, 3, 4. 6 minus 4 plus 2 is going to be 0. Okay, now we're going to go for HNO2. The first thing we always do is to count the valence electrons in the overall molecule. So hydrogen has 1, plus nitrogen has 5, and we have 2 oxygens, each have 6 valence electrons. 1 plus 5 plus 12 is going to be 18. Now, as you see, we cannot have 2 oxygens attached to each other. That never works. So it's better to attach them separately to the central atom. So in this case, hydrogen cannot be a central atom because it only has 1 electron available for bonding. So we're going to go with nitrogen as our central atom. In this case, we attach one of the oxygens to nitrogen with a double bond because we want to fill up all the oxygens. We want to reach to the octet with one of the oxygens at least. And then we have 1 electron left on the nitrogen, and we're going to make a single bond between that nitrogen and that oxygen. But if you see, the oxygen is going to have 1 electron left, and that is where you use hydrogen to make a single bond with oxygen. So basically 1 oxygen with double bond with nitrogen, and once 1 electron is left on the nitrogen, you attach it to the oxygen and the hydrogen would go to the oxygen. Now in this case, after we do all this, we start counting the formal charge for each atom. We start with oxygen with double bond. Oxygen originally has 6 valence electrons minus 4 electrons in the lone pair plus 2 bonds. 6 minus 4 plus 2 is going to be 0. Now we do for nitrogen, 5 valence electrons for nitrogen minus 2 electrons in the lone pair, and also it has 3 bonds with oxygens around it. 5 minus 3 plus 2 is going to be 0. Now let's go for the oxygen again. We don't need to do hydrogen. Now let's go for the oxygen again. It has 6 valence electrons minus 4 electrons in the lone pair plus 2 bonds. It's going to be 0 again. Now we can see another, like we can make another structure to see if there's any other structure which is more stable than this one. As you see, all the atoms on this one have the formal charge of 0. Basically seems stable. We're going to do other forms as well. The second structure we're going to do is to put nitrogen as a central atom, and we're going to add the hydrogen to the nitrogen as well, instead of attaching it to another oxygen. So as you see, the nitrogen attached to an oxygen with a double bond, and a single bond with another oxygen. This time we're going to give this oxygen 3 lone pairs because it has to reach the octet. And when we don't attach the hydrogen, 1 electron is left. So we're just going to give it another electron. 1, 2, 3, 4, 5, 6. And the bond makes it 8 octet. And now we attach the hydrogen with a single bond to nitrogen. Now we're going to start counting the formal charge for each atom again. Oxygen with double bond, as you see, 6 minus 4 plus 2 is always 0. Now, we go with a single bond. As you see, 6 minus, we have 6 electrons in the lone pairs, plus 1 bond. It's going to be 6 minus 6 plus 1. It's going to be negative 1. Now we go with a nitrogen. This is going to be interesting. Nitrogen has 5 valence electrons, right? 5 minus 0 lone pairs, as you see, so 0 for that. And 4 bonds. 5 minus 0 plus 4 is going to be plus 1. The atoms here, not all of them are 0 for formal charge. So that shows instability. Let's try another structure. This is the third structure that I'm going to draw. This time, we're going to attach the hydrogen to the oxygen with a double bond. So the first oxygen is going to have 3 lone pairs attached with a single bond to the nitrogen, and on the other side, the nitrogen is going to be attached to the oxygen with a double bond, and the hydrogen is going to be attached to this oxygen. Now, as you see, I said octet rule all the time. The first oxygen has to have 3 lone pairs and 1 bond. In this case, it has 8 electrons at the end. The nitrogen, 1, 2 for the lone pair, and 3, 4, 5, 6, 7, 8 on the bonds. Like 3 bonds, 3 times 2 is going to be 6, plus 2 on the valence on the lone pair, it's going to be 8. So nitrogen has reached the octet as well. Now we go for the oxygen with double bond. 3 bonds, 3 times 2, it's 6, and a lone pair, 8. So far everything seems to be good as a matter of octet rule. Now let's count the formal charges. The oxygen, 6 valence electrons, as we said, minus 6 electrons in the lone pair plus 1 bond. 6 minus 6 plus 1 is going to be negative 1. Now let's do nitrogen. 5 valence electrons minus 2 in the lone pair and 3 bonds. 5 minus 2 plus 3 is going to be 0. So nitrogen seems to be good in this one. And now we go with the oxygen. 6 minus 2 plus 3 plus 1. As you see, 3 bonds and 2 electrons in the lone pair. 6 minus 2 plus 3 is going to be plus 1. So when we have a structure that all atoms have 0 formal charge, that is the most stable one. That doesn't mean that the other ones don't exist. Might exist, but they're very unstable. They're not going to last so long. Now we're going to go with molecular shapes. In this part, we're going to use a VSEPR theory. And as you remember, VSEPR theory was giving us the structures that we could predict the bond angles and also the overall molecular shape of each molecule. This one we're going to show it with AXE. Now for X, the number of X, we're going to show it N. With the number of E, we're going to show it M. So A is the central atom. Usually in organic chemistry, the central atom is carbon. We saw like it could be nitrogen as well, but most of the time it is carbon. X is the neighboring atoms, and the number of it is going to be determined by N. And E is the lone pair. In VSEPR theory, we're going to show the lone pairs as well. So let's start with the table. In the first one, N is 2, M is 0. That means AX2. One central atom with 2 neighboring atoms, 0 lone pair electrons around it. So we're going to draw the A with 2 X's around it, just like a line. The next one, we're going to have 3 neighboring atoms, still no lone pairs, AX3. And we're going to draw it like this, A, and 1x on top, 1x down here, and 1x down a little bit to the right. It's like a trigonal. Now we go to the next structure, 2 neighboring atoms. This time we're going to have 1 lone pair. So we write the formula as AX2E1. Now I want you to know, before I go to the structure of this, the bond between the A and X, you see there's a line. This is not necessarily a single bond. In VSEPR theory, we don't show double bond or triple bond because we are not sure what the atoms are and what molecule we're talking about. These are just the shape of molecules that we can have. So these could be a double bond, a triple bond, a single bond, but we're just going to show it with a line in VSEPR theory. So as I said, AX2E1, that means we have 2 neighboring atoms. We draw that with a lone pair instead of one of those atoms in the previous structure. So this is like exactly like trigonal that I showed in AX3. Instead of 1 neighboring atom, I just put 1 lone pair. Lone pairs have the power to bend the angle of the bonds between the neighboring atoms, so we treat them as 1 atom, like a neighboring atom. Let's go to the next structure. If we have 4 neighboring atoms and 0 lone pairs, so AX4. The way we draw this, we put the central atom, 2 x's on the side, 1 x down, and 1 x on top. As you see, it might look different than Louis' structure. That is fine. We're drawing this in order to find the name of the shape and also the angle between each bond of the neighboring atoms. And we're going to get to that in a little bit. If we have 3 neighboring atoms and 1 lone pair electron, we're going to have AX3E. We're going to draw the exact same thing that we drew for the previous one. Instead of one of the x's, we're just going to replace it with a lone pair electron, as you see here. We usually put the lone pair electrons on top. You don't have to. That's usually the way everyone does. It's a common way of doing it. And we get to the next one. If we have 2 neighboring atoms and 2 lone pairs, AX2E2. In this case, the bond angle between the 2 neighboring atoms is going to be slightly smaller than the previous ones, and we're going to replace 2 of the x's with 2 lone pairs. Now a good example of this is water, H2O. Oxygen has 2 lone pairs and 2 hydrogens attached to it as neighboring atoms. Okay, now since we drew all the structures, we're going to talk about the angles between each neighboring atom. Okay, so now we're done with the structure. Let's do the angle between the bonds and naming each structure. So as you see, the first one, AX2, there is no lone pair, only 2 neighboring atoms. So these 2 neighboring atoms are going to be as far away as possible from each other because there is no lone pair to push them together. So this one, they're going to stand in a 180-degree angle from each other, and the naming of it is going to be linear because it's like a line. An example of this is basically CO2. The carbon doesn't have any lone pairs, so the oxygens are going to stand in 180 degrees from each other. The next one is AX3. No lone pairs again. Now the only force that keeps them away from each other is the electrons of the neighboring atoms. So in this one, we're going to have a 120-degree angle between each of the neighboring atoms. This one is called trigonal planar. Next structure is AX2E1. As you see, there's a lone pair here. The angle between the 2 x's is not going to be exactly 120 degrees. The lone pair electrons can put more pressure on the 2 neighboring atoms, more than 1 atom on top. So in trigonal planar, the pressure from 1x on the other 2 is not as much as the pressure that a lone pair can put on the 2 neighboring atoms. So here, the angle between the 2 neighboring atoms, the 2 x's, is going to be less than 120 degrees. Slightly less. It's not going to be like 90 degrees or anything. Slightly less than 120 degrees. However, this one is not going to be linear anymore, and it's not trigonal planar. Why? Because a lone pair is not going to affect the structure, the 3D structure of it, as a matter of having neighboring atoms around it, the way the second one had, the AX3. So we call this one a bent molecule. Okay, the next structure is AX4. a central atom with 4 neighboring atoms around it with no lone pair. This one, as you see, between each neighboring atom, the angle is 109.5 degrees exactly. The structure of this one is called tetrahedral. Now, some of you might think, why is it not 90 degrees? The thing is, the molecules are not shaped in a two-dimensional world. It's a three-dimension, so you should think of it as a sphere, not a circle. The next structure is AX3E. 3 neighboring atoms with a lone pair. Now, as you see, we're going to draw it exactly the same way we drew the tetrahedral. We're going to replace one of the X's, one of the neighboring atoms, with a lone pair. Now, as I said before, the lone pair has more power to push the neighboring atoms than an atom itself. So basically, the angle between 2 neighboring atoms is going to be less than 109.5 degrees. The name of this structure is not bent or tetrahedral. It is trigonal pyramidal, because if you think of it in a 3D shape, it is more like a pyramid. And we get to the last structure, AX2E2. 2 neighboring atoms and 2 lone pairs. Now, as you see, we put the 2 lone pairs electrons on top and 2 neighboring atoms in the bottom. So as I said, this is like water. Now, since we have 2 lone pairs, it's going to be even more pressure than trigonal pyramidal. So it's going to be even less the angle between the 2 neighboring atoms in 109 or 109.5 degrees. In this one, it's usually between 105 to 108 degrees. Now, this is not a pyramid because it only has 2 atoms attaching to the central atom. So we just call this a bent molecule. Okay, now we know all the angles, all the shapes. Now we get to polarity. We're going to make one column for the times that all of our neighboring atoms are the same, and one column for the time that we have 1 or 2 different atoms in our neighboring atoms in our molecule. So let's start with the first one. AX2. Let's say both X's are fluorine. So it's basically AF2. We draw it in a linear form, as you see. Now here, the bond between the A and F is polar, absolutely, because let's say if A is carbon and fluorine is like is a halogen, the difference between electronegativity makes this bond polar, but that does not mean the molecule is polar. So why is that? First of all, there is no lone pair. And secondly, the polarity of each bond is cancelled because these guys are linear. So the dipole moment created between AF on each side cancels out the other one. So what if we have a different atom for one of our neighboring atoms? Let's say AFH. Instead of one of the fluorines, we have a hydrogen. Hydrogen is not as electronegative as fluorine. In this case, we only have the dipole moment on one side of our molecule between the AF. So the polarity is going to lean toward the fluorine. And in this case, our molecule is going to be polar. Now I want you guys to remember, a polar bond is not necessarily an indicator of the polarity of a molecule. Polarity of a bond is dependent on how electronegative each atom is, while we have different criteria for polar molecules. Let's go to the next one. Now we go with the second structure. Okay, so as you see, it is a trigonal planar. If we say, like the first one, all the surrounding atoms have a dipole moment, they're going to cancel each other out if you add them up. So in this case, this is going to be non-polar again. There is no lone pair as well, so we can strongly say it's a non-polar molecule. Now, what if one of the neighboring atoms is different? We replace the top one with hydrogen. Now we're going to have 2 electronegative bonds with a dipole moment on the surrounding atoms, on the neighboring atoms. So the overall dipole moment of the molecule is going to head to the downside of the molecule. In this case, it is going to be polar, because the top atom, which is hydrogen, is not going to have a dipole moment to cancel those 2 out. Let's go to the next structure, AX2E1. So in this one, they have a lone pair. For a molecule to be polar or non-polar, if it has a lone pair on a central atom, it is 100% polar, regardless of the neighboring atoms being the same or different. And I can say, yes, the dipole moment might be the same, but since it has a lone pair on top and it bends it, it's going to be 100% polar, and the polarity is going to be more towards the lone pair on top. Let's go to the tetrahedral structure. There is no lone pair. That means if it is the same, we might have a nonpolar. So let's look at it. We have 4 neighboring atoms with the same electronegativity and the same dipole moment on their bonds. In this case, they can cancel each other out. So at the end, it's going to be a non-polar molecule. What if we replace the top neighboring atom with a hydrogen? Now, as I explained, look at the second one, the trigonal planar. All the dipole moments in the other 3 neighboring atoms is going to head toward the downside. And there's nothing up there to cancel them out. So it's going to be polar. As you see in the next structure, it has a lone pair. Regardless of the neighboring atoms being the same or different, it is going to be polar again. We don't need any other reason for it. It is polar whether it has the same neighboring atoms or different neighboring atoms. Same thing with last one. This one has actually 2 lone pairs, so it's 100% polar.